we have a sphere of radius r capital. Then there is a charge q. Let's assume it's positive charge, uniformly distributed over the whole sphere. Uniform distribution. Of course, yeah, we're just looking at the simplest possible situation. Of course, the distribution of charge can be more complicated, but it's still reasonably simple if you have not uniform distribution, but still spherical symmetry. Even in that case, application of the Gauss's law is reasonably simple. Of course, integration will be more complicated, but the procedure will be pretty much the same, with more complicated integral. But anyway, so here we have uniformly charged dielectric sphere, right? It's not a metal, it's not a piece of metal. Metals will be discussed later, right? Okay, so that's what is given, and what we need to find electric field. We need to find expression for the electric field outside of the sphere and inside. Okay, I will write A. There will be two parts. In the first part, in part A, we will find electric field outside of the sphere, and then in the second part, inside. Right. So let's find electric field, question mark, and I will write outside, where r small is larger or equal r capital. Outside or on the surface. Right? Okay, so, and as I just told you, I want to emphasize that now we have two alternative, equally strong approaches which can be used to find electric field. Either Coulomb's law with the probe charge or Gauss's law. In this case, although we have a nice symmetry, application of the Coulomb's law, right, integration like we did what a couple of classes ago. In this case, it will be significantly more complicated relative to the Gauss's law. But application of the Gauss's law over here, it's just pleasure to use. So we're going to use Gauss's law. So if we want to use Gauss's law, of course, first of all, we need to write it. E dot dA equals to Q enclosed over epsilon naught. Okay. What do we have to do first? Which step do we have to make first? Without that step, we will never be able to move any further. The first step, think for a second, right? Without that step, we will never be able to do anything. Look, integration is done over what? In order to integrate that, we need to know surface, because this is integration over a Gaussian surface. Then also, in order to find Q enclosed, in order to see which charges are enclosed, we need to know a Gaussian surface. So the first step in application of the Gauss's law, we must pick a Gaussian surface. Otherwise, you cannot start taking this integral, because the surface is not, you haven't decided over which surface you want to integrate. And of course, you wouldn't be able to write the value of Q enclosed if you don't know which surface is used. Right. First step, Gaussian surface. Right. Okay, which surface can be used as Gaussian? Okay, let me first write a Gaussian surface. Okay, which surface? First of all, Gaussian surface must be in the region where you want to find the electric field. It makes sense. It's like if you want to sample the life, I know, in Canada, you don't go to Madagascar, right? You go to Canada in order to sample life, the level of life, or so on, right? And the same here. If we want to find electric field outside of the sphere, of course, our Gaussian surface must be outside. And of course, it must be closed. Then, of course, you can, as I keep telling you, you can use any closed surface as a Gaussian surface. Virtually any surface your soul desires, right? Or, I don't know, heart and kidney desires, right? And you will never be wrong with any surface. For example, let's say you decide to use a surface like this with very complicated shape, right? I will never be able to tell that that is a wrong choice of the surface. Never. Because, yeah, Gauss's law can be applied for any surface. But the thing is, we need to solve this particular problem. We need to find the value of the electric field, expression of the electric field, right? And with your kind of correct surface, you will never be able to complete this problem just from the mathematical point of view. So in this case, the fact that you are correct is useless. You will never be able to solve the problem. So on top of being correct, we must be wise and pick the best possible out of infinite number of possible options for the Gaussian surface. We need to pick the best one so that the amount of mathematical work will be minimum, and so that we can use the symmetry of the problem. Because with a complicated choice of the surface, you will never be able to use the symmetry of the problem, right? So we need to pick the best Gaussian surface. And you should be able even to guess what is the best Gaussian surface, right? It will be the best Gaussian surface is a concentric sphere of radius larger than r capital. Over here, concentric, it means centers of both spheres are the same spot, right? So the best Gaussian surface in this situation is the concentric sphere. And I will justify it when we start going through the solution. I will justify this choice. Right. Okay, so the best Gaussian surface, I will use a green dash line. So that's my Gaussian surface. Okay, let me do it this way. So this is my Gaussian surface. Okay, it's slightly distorted, but it's a concentric, it's a sphere. I didn't graduate from an art school. I graduated from the physics department, so that's why it's slightly asymmetrical. But anyway, and of a some radius r small. Basically, r small, it's sort of like a variable. It's some arbitrary radius r small. And of course, this r small is larger than r capital. Okay, so that's the first step. Now, after this step, we can start actually evaluating the left-hand side and right-hand side. So usually I start taking care of the left-hand side first. Okay, so integral of the closed surface. Okay, closed our Gaussian surface E dot dA equals. Okay, now I will pause because now the most difficult part almost. We need to take this integral, which is again calculus integral from from the calculus 3 course. And of course, you don't know how to take these integrals, but nevertheless, we will still be able to take this integral. Okay, in order to take this integral, let's first draw all these vectors on a picture. Electric field vector, area vector, and so on. And again, you need to remember that in this integral, all the time we are on this Gaussian surface. We're not on that surface of our charged sphere. No, because very often students just draw these vectors on that charged surface. No, we are on the Gaussian surface. We're not allowed to step away from this Gaussian surface. According to this law, we are on the Gaussian surface. Right? Okay, so let me first draw dA. Right, and you remember the convention. The area vector must be perpendicular to the surface and point towards the outside. Towards the outside because of the convention. You remember in the previous class when we were discussing the electric field. So, if for example I take this patch, small patch, right? It's a dA, right? It's basically what? It's a cross section of the sphere, right? So let's say this is my dA. Right? And all right, so of course it must be perpendicular since this is sphere. Perpendicular, it means the dA will be radial. Okay, so that's my dA vector and points towards the outside. So, and so of course, since during this integration, we're going to take care of all the patches on this green surface. Oh, let me draw a few other vectors on a few other patches. For example, let me take this one. Here will be dA, right? Over here I can take one. So this is my dA, and so on. Of course, you can draw as many as you want, but usually one or two is enough. Okay, so now we see direction of dA. Now, what about electric field vector? What's the direction of the electric field vector? Usually books say something like this. It's obvious because of the spherical distribution of charge that the electric field will be radial. Basically, radial, it means like this way, right? I usually draw an additional picture to make it clearer, to justify, okay, in my opinion, maybe slightly better, right? Not just with words. Okay, so let me now give you a small justification of a radial direction of the electric field. Okay, let me draw underneath additional picture. All right, so let me write justification of radial E direction. Okay, let me do this way. Let me redraw this picture smaller. So let's say this is my charged sphere. This charged sphere of radius r capital, right? Okay, let me even show. Maybe this is r. And let's say, for example, I want to find direction of the net electric field at this point. Okay, let me draw auxiliary line which goes through the center of the sphere and through the point where I want to find direction of the electric field. And since this sphere is uniformly charged, so we have charges at every point, so let me take, for example, small piece of charge over here, completely arbitrary point. Just small piece of charge, right? And basically point charge. And of course, we know electric field lines over point charge, right? They're radial, right? And so let me draw contribution from this point charge to the net electric field from this point. Now, at this point, we can do that easily, right? So let me draw dash line. And of course, the electric field will be this way. But at the same time, I can find symmetrically positioned charge, symmetrically relative to this line, position charge over here. Also point charge. Because we have uniform distribution of charge, we can find point charges pretty much anywhere we want. So I decided to look also at this symmetrically position. And now let me draw contribution to the net electric field from this point, from this blue charge. Okay. Okay, of course it will be this way, E. And now let's add these two vectors. Of course, radial components, this radial component, and, oh, not radial, sorry, tangential component, this tangential component of the blue field, and tangential component of the red field, they cancel each other out. And if you add these two vectors, okay, let me use red, all right. And if you add the radial components, of course, they will give us this net electric field, all right, pure radial. So pretty much for any charge over here, I can find symmetrically positioned charge, and their tangential components are going to brutally cancel each other, leaving only radial components. So pretty much it doesn't matter which point I take, here, 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 or anywhere around the charge sphere, electric field is going to be radial. All right. So pretty much. That's why usually books usually say, right, because of the spherical symmetry, the electric field is going to have only radial direction, right? So I can draw basically here, 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 electric field lines, right? But I'm not going to draw those lines. I'm going to draw just electric field vectors next to these dAs. Okay, so let me draw here, E, here, E, and maybe here, electric field. Okay, so now I see pretty much almost everything about the electric field. Okay, I see directions. Let me see. I see directions of E and dA. So now I will open my explanation box and write so E, or I can say since E is parallel to dA, right, you see, the same directions, I can simplify this dot product or scalar product. So I can write E dot dA equals to E dA n times cosine of angle. I'm just writing explicitly dot product of two vectors, EDA. Okay, let me just finish this line and then we'll have a break. So absolute value of E, absolute value of dA, and then cosine of angle between these two vectors. What is the angle between these two vectors? These two parallel vectors, the angle between them is 0 degrees. 0 degrees. So as a result, I can write this cosine of 0 degrees is 1, so it will be just E dA. Let me close my explanation box and let me continue over here. So now instead of this integral, I can write integral of E times dA. What's the major achievement over here? Here we have products of vectors. This is vector, that is vector. Now after this first step, now it's the magnitude of E and magnitude of dA. So now we have just the product of two magnitudes. They are no longer vectors. There's a scalar function. No vectors. So that's the achievement of the first step. And okay, let me hold you for extra minute. So now next step, in order to take this integral, now this is the absolute value of E. Let's imagine you sit over here on this patch. Imagine yourself sitting on this patch on the Gaussian surface, right? This electric field, and here we have magnitude of that electric field, right? This electric field is created by what? By this distribution of charges. So look at those charges, remember, and now let's move yourself to the different point. Let's, for example, move yourself to this point. And look at the distribution of charges from this point. Will it be the same as distribution of charge you saw from this point? Of course, because of the spherical symmetry, distribution of charge, if you look from this point, will be exactly the same. It means what? If your distribution of charge is exactly the same, it means what? It means that electric field strength at this point will be exactly the same as here. Magnitude of the electric field strength, of course, directions are different. Electric field direction over here that way, over here will be this way. But we need to know about the magnitude, and the magnitude of the electric field over here, here, or any other point. You can move yourself to this point. Again, distribution of charge will be exactly the same. And of course, electric field, magnitude of the electric field strength will be the same. So basically, I'm claiming, because of the spherical symmetry, electric field magnitude at any of the points on the Gaussian surface, because again, in this integral, we are staying on the Gaussian surface, right? Electric field strength is the same. Not vector, strength. At this point, I couldn't say that, because here we had a vector, and vector had different directions. But once we managed to get rid of a vector, now it's a magnitude, strength. Now I can use this fact, okay, electric field strength is the same. And if now, so as a result, so this E is constant on the Gaussian surface, right? and what can be done with a constant inside of the integral, constant factor, right? We can take it outside. We can extract it. You remember I told you about the problem with the Gauss's law. Major problem, it's difficult to extract the electric field from the sign of integration. But in this case, because we have a nice spherical distribution, extraction is trivial. So now we can extract this electric field, and this is the most important point. So now, okay, let me again open my explanation box, and I will write, since electric field is constant, and I will add on the Gaussian surface. Because in this integral, we stay on the Gaussian surface. Sometimes I see students write, because electric field is uniform. No, no, no. Uniform electric field, you remember, it's exactly the same at any point in space in the same direction. But here, direction's obviously different, right? And about the strength, if you, for example, step away from the Gaussian surface, move closer, electric field goes up. Strength, electric field strength. If you move farther away from the Gaussian surface, of course, electric field becomes weaker, right? So you see, electric field is not uniform. Here, electric field just a constant on the Gaussian surface. Basically, we use the symmetry. We utilize the property. Use the symmetry of the problem. Okay, so since electric field is constant, we can extract it. As a result, we are getting that E integral over the closed surface dA. Okay, so and now let's have a break. And now you can tell me what's the value of this integral. Okay, from this point we will continue after the break. Okay, let's get back to at it's 8:55. Okay, 9:04. That's 9:04. We'll continue this problem. Okay, guys, if something not clear, we have 10 minutes to discuss, and of course we can discuss as much as we want after the class, right?
Just have one question about that. So E can only be factored out outside the integral if it's a perfect circle, correct?
No, I wouldn't generalize that way. I would say if electric field is constant, whatever situation is, if electric field is constant on your surface, then you can extract it out of the sign of integration. But in this case, yes, because we picked the best possible surface. If you pick, instead of sphere, ellipsoid, which is absolutely correct, nothing wrong with using ellipsoid over here. But in that case, if you have an ellipsoid, okay, let me draw another picture. If you have an ellipsoid, so let's say this is your charged surface, all right, plus, 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 and let's say you pick an ellipsoid. This is your Gaussian surface. Look, over here, electric field will be obviously stronger than electric field at that point, right?
Yeah.
Because this point is farther away. So in this case, if you pick this surface, this ellipsoid, again, I would never be able to tell you that, no, you cannot use the surface, you are wrong. No, you will be right, you would be right, but you will never be able to use all the steps. It means that your mathematics will be ridiculously complicated. And I doubt that you would be able to finish this problem and solve it. Again, you will never be wrong, but you will get very low score and points, right? And because you will never be able to solve the problem, you will never be able to achieve the goal, right?
All right, that makes
That's
sense.
why in these problems, the most important step, the first step, right? You need to pick the best possible Gaussian surface. Otherwise, you will never be wrong, but you will spend half of your life, right, solving a simple problem, right, instead of solving it using, I don't know, in 5 minutes.
Mm-hmm.
And plus, even in this case, the first step, you would never be able to complete the first step. Because, electric field will be still radial, right? Because we cannot change with our imaginary Gaussian surface, we cannot change direction of the electric field. It's a wishful thinking. right? If we, with our imagination, we can change direction. No, electric field will be still radial, right? So electric field, oops, will be still like that, right? But what about the area vector in this case? For this ellipsoid, area vector over here, it will be in the same direction as the electric field, right? So let's say this is dA. But over here, dA will be that way. Over here, dA will be that way. So you see, dA and the electric field are no longer parallel. They will be parallel only in a couple of spots, maybe in a few spots, right? As a result, we wouldn't be able to use this step. We wouldn't be able to use this step, right? So, but since we pick concentric sphere, this is possible. This is correct. This is correct. But even with the ellipsoid, it's already becomes significantly more complicated.
Yeah.
Okay, let's continue. It's 9:04, and so what's the value of this integral? What's the answer? Okay, again, I keep telling you this. I keep telling you the same thing. Strictly speaking, from the mathematical point of view, this is still not it's not a trivial integral. It's still calculus 3, and at some point you will learn how to handle this integral, right? But we know the meaning of this integral because electric field now is outside, and what we have integrating over the closed surface over our Gaussian surface dA. Since now we should be able to, we understand the meaning of this integral, we should be able to tell the answer. Again, what is dA? It's the area of the small patch, of a small patch on the Gaussian surface. So, and again, what's the meaning of an integration? Integration is just a fancy word for adding small things, small contributions. In this case, small contributions to the total value of the integral, right? So, small value of dA, small area, plus next patch, again, area of this small patch, plus area of this small patch, plus, and you keep adding small areas of all these patches. And when you complete the whole surface of the Gaussian surface, what are you going to get? The total surface of your Gaussian surface. No, it doesn't sound right. The total area of the Gaussian surface, right? The total area. And of course, we know the radius of our Gaussian surface. Its radius r small. So what's the answer? We all know from high school, the area of a sphere. 4 pi r squared. Okay, guys, I'm telling you, lots of mistakes on the exam at this point usually. Okay, let me write that down. So this will be equal to 4 pi, and again, careful, r small squared, because lots of students just pick whatever radius is they see r capital. No. We are on the Gaussian surface in this integral, so it's the area of the Gaussian surface. So we need to use radius of the Gaussian surface, r small. 4 pi r squared. Typical mistakes at this point. Students use area of the circle, circumference of a circle. There's some, no, at this point, using the wrong formula for the area of the circle, no, it's a little bit too much, right? So if you're not confident, somewhere at the end of your notes, notebook, right, create a table, right? So area of this, area of that, area of volume of sphere, right, and so on. Lots of silly mistakes at this point, right? Okay, so just we know the from the meaning of the integral, we know that this is the area of the sphere, Gaussian sphere, our Gaussian surface. So it's a 4 pi r squared. So you see, we managed basically to take the integral without actually taking it, because we've made first two preliminary steps, extracted electric field, and now it's just the area of the sphere. So it's equal to E times 4 pi r squared. So what we just found, let's connect with what we discussed on Friday. It's the value of the electric flux. It's the value of the electric flux through this closed Gaussian surface. It's a number of electric field lines crossing this Gaussian surface. That's what we found. That's the electric flux, right? And yeah, again, back to the extraction. Look, usually I call this first step in the extraction of the electric field. It's sort of like a preparation for the extraction. We managed to get rid of vectors, and now it's just the absolute values. And then the second step is the actual extraction. It's like in a dental office. Before they extract the tooth, first they use anesthesia, right? So this is like anesthesia, and then the actual extraction of the truth, or extraction of the electric field, right? Okay, so that's the value of the electric flux. And now back to our Gauss's law. And according to the Gauss's law, it must be equal to Q enclosed divided by epsilon naught. Equals to Q enclosed divided by epsilon naught. So that's now what we have. Then at this point, I usually ask, okay, guys, find the value of the Q enclosed. Q enclosed, because now we found the left-hand side. Now we need to know the Q enclosed. And I know typical, very, very typical mistakes. I know 30% of students, maybe slightly less, 25, 30% of students, they made this mistake. At this point, when they see the question, find Q enclosed, here is what they do. They just solve this for Q enclosed in terms of E, in terms of electric field. I would never be able to say it's wrong, but it's useless. In this equation, we have how many unknowns? E, that's our final goal, that's what we want to find eventually. And Q enclosed. If you write one unknown in terms of the other one as the answer, it's useless. So pretty much for that question, students get immediately 0, nothing. So what do you need to do? Somehow using some other reasonings, you need to find Q enclosed, and then once you know Q enclosed, you can solve it for E, the final goal. But now we need to somehow find Q enclosed using the meaning of Q enclosed. So now let me write Q enclosed. And actually, I'm not surprised that some students make this mistake, because some students just don't come to class, they do something else during the class, right? So as a result, they need to write something on the exam, and they write the first obvious thing. All right, so Q enclosed, the meaning, you remember, it's the total charge within, inside the Gaussian surface. So at this point, by looking at the picture, all of you should be able to tell me what's the value of Q enclosed. Again, it's the total charge physically embraced by your Gaussian surface. And again, you remember, where those charges are doesn't matter. Gauss's law doesn't care. You remember we discussed properties of the Gauss's law. Distribution of charges doesn't matter as long as that charge is inside of the Gaussian surface. Our Gaussian surface over here, so the total charge sphere is inside. Do we know the total charge inside of that charge sphere? Yeah, it's given. It's Q. And it's all within the Gaussian surface. So Q enclosed is total charge Q. In this case, it's trivial. So Q enclosed, in this case, Q. And again, guys, sometimes I see students write the final answer, because after this we can just solve immediately for E. They write the answer in terms of they just write Q enclosed. No. Q enclosed shouldn't be in your final answer. What should be in your final answer? Q without any subscript and R. The final answer must be written in terms of what is given and the variable. In this case, variable is R small, right? Because we're going to get electric field as a function of R. Right. Okay, so now Q enclosed in this case is trivial, is just Q. Okay, so now basically we're almost done. Let me just rewrite it in terms of Q. So it will be E times 4 pi r squared equals to Q divided by epsilon naught. So now that can be solved finally, and that will be our final expression. Now I will write it E as the function of r. Right. E as a function of r. So it will be Q over 4 pi epsilon naught and r squared. So, and of course that is for r small, larger or equal, r capital. That's for the outside. So let's frame it. Of course, we almost spent like half an hour solving this, although strictly speaking, it can be done in 2 minutes. Right. But of course, every time I'm trying to justify every step, explain every step, right? So I'm trying to be as thorough as possible. But of course, yeah, it can be done. Yeah.
I just had one clarifying question to make sure I understand it. So, are you replacing integral dA with 4 pi r squared because you're representing the surface area, and like that's a different way to represent the area under the curve of the circle?
Basically, okay, yeah, I can say that, yeah, you are correct. Basically, this is I explain the meaning, right? So the meaning of this integral, it's the area of the surface. In our case, the surface is a sphere. What are my neighbors doing? Are they dancing or what? Some noise. Okay, so the meaning of this integral, it's the area of this of the Gaussian surface, and of course we know from high school, we just use high school knowledge. It's a 4 pi r squared. It's the same story like what 2 classes ago when we were finding the value of the electric field created by, where is my ring? Where did I? There it is. All right. So you remember we were finding electric field created by a uniformly charged ring, right, at the distance d. We used basically the same idea. You remember at the end we had integral. We had something like this integral of dl. You remember we had an integral of dl, right? And again, this is not a trivial integral, but we knew the answer, and the answer was what? Circumference of the ring, 2 pi r. And the answer was 2 pi, I think it was r capital, right? The same here, right? So we just knew the meaning of this integral. Now over here, we know the meaning of this integral, and using the high school knowledge, we know the answer. But of course, in calculus 3, if you when you see the integral like this, and if you just write the answer, instructor will never accept it. You need to show all the steps, show the patches, show integration over phi, over theta, over say what's so special about r, and so on. Yeah, still inside of this, lots of work, but we know the answer. Okay, is it enough? Okay, is it good enough?
Yes, thank you. Yes, thank you.
We just use the high school knowledge. Okay, so that's the part A. Now let's do part B. Let's find electric field inside. So now I use blue. So now basically part A and now part B. Right, so part B, we need to find still electric field, but now it is inside for r small, smaller or equal to r capital. Okay, so now I'm thinking, you know what, I will recycle the same picture. Again, we will use Gauss's law. Right? Again, it will be integral of the closed surface E dot dA equals to Q enclosed over epsilon. And again, the same. The first step must be the first step we need to, first of all make a decision which Gaussian surface we're going to use. Right. Again, without that step, we wouldn't be able to move any further. And again, since now we're interested in the electric field inside of the sphere, our Gaussian surface must be inside. And be careful, because again, in the past, when we were at school, right, and whenever I give a problem similar to this on the quiz or exam, some students just the question is about finding electric field inside, and they draw and use Gaussian surface outside. So guys, careful, don't make those silly mistakes also, right? Be careful, read the problem and pick the Gaussian surface. So our proper Gaussian surface, so our Gaussian surface must be inside. And again, I think now I don't have to justify that the best Gaussian surface will be another sphere, but now inside. Again, sphere, concentric, Gaussian sphere will be concentric with our charged sphere, but now it will be inside of our charged sphere. Okay, so now let me draw. You know what? I can probably use. Yeah, I have a bunch of plates which I used to draw pictures. This is container. It's a takeout container. I think it was from one Indian restaurant, I think. So I use them. Okay, so this will be. This will be my Gaussian surface now. Right. And again, of some arbitrary radius r small. But of course, now r small is smaller than r capital. And all right, so this is also a Gaussian surface, right? But for part B. So this is for part B. Now, from this point, once you pick a Gaussian surface, okay, let me write again, Gaussian surface. The rest of the steps, these steps, up to this point, will be exactly the same. Not a single symbol is going to be different. So over here, you can just rewrite all these up to this point. Of course, I'm not going to do it. And of course, now dA will be over here. Let me draw a few dAs, right? So let's say this is my dA, right? But now, of course, it will be on this Gaussian surface. Electric field will be still radial. So this will be electric field and dA for part B. So all these steps up to this point are going to be exactly the same. So I will write in exactly the same way. Okay, after exactly the same steps, after exactly the same steps, we'll get, I will just write this part which is underlined, exactly the same. So it will be E times 4 pi r squared equals to Q enclosed over epsilon naught. And now, basically, again, we just calculated the electric flux in terms of, as a function of r. And now we just need to take care of Q enclosed. So the next step, what about Q enclosed? Okay, so this is now part about finding Q enclosed. This is the place for the largest number of mistakes. I would say more than 50%. More than 50%. right? Although it's not that complicated, right? Again, we just need to use, you remember that slide about charge densities? You remember there were three parts: one-dimensional case, two-dimensional, three-dimensional. In first case, we discussed a linear charge distribution, then surface density, linear charge density, surface charge density, and then volume charge density. We need to use that again. And I told you back then that we would need those formulas when we start discussing Gauss's law. Here we started discussing Gauss's law, and now we need to use those formulas again. Right. So now Q enclosed in this case. So first of all, we need to see on the picture where is this Q enclosed. Again, it's the charge, total charge, within your chosen Gaussian surface. Now your Gaussian surface is here. So the charge which we want to find is this. Let me highlight it sort of like this way. So this is where our Q enclosed. Again, that's for part B, for this part B. You see? Again, it's just the total charge physically embraced by Gaussian surface. This is our Gaussian surface, so that's the amount of, that's where Q enclosed is, right? I doubt that you disagree with that. Right? Okay, so now, and it's obviously that this Q enclosed is less than Q, is less than this Q which we used in part A. So now we just need to find that smaller amount of charge. Right? Okay, so now we are going to use those formulas from that slide which I just mentioned, which I just mentioned, right? So you remember in the third part about the volume charge density, I told you first. Okay, actually, it's the second formula in the third box, right? About three-dimensional case. So where I told you, if you want to find some amount of charge, the amount of charge in the small volume dV, right? It was you need to take charge density. In that case, it was volume charge density rho, right? So we had something like this rho, volume charge density, and multiplied by dV. That was infinitesimally small portion of the charge, of the volume. But in this case, we want to find the amount of charge in this volume. So it's not dV. We can easily write the volume of the Gaussian surface. So now I will remove this dV, like what we had in that formula, and we can write we can write the volume of, okay, that's not the good V. Right, so V with the radius r small, and that's our Q enclosed. Basically, that's the second formula from three-dimensional case. But now instead of dV, we have the volume of the Gaussian surface. All right? And it's like with the mass density. Let's say I know my density. Let's say I have uniform mass distribution, right? Let's say I have, I know, 5 kilograms. No, it's too much, right? I know 100 kilograms. Again, it's too much, right? Okay, 100 kilograms per cubic meter, right? And then let's say I know the volume of my hand and I want to find the mass of my hand. So what do I have to do in order to find the mass of my hand? I take my density and multiply by the volume of my hand. It's the same story here. But we just need to replace mass with charge. That's it. So volume charge density times the volume of the Gaussian surface, because because inside of that volume our charge Q enclosed. But of course, right now we don't know volume charge density. But can we find volume charge density? Again, it's the first formula on that slide. So now, since volume charge density we don't know, but we can easily find it. Again, I open my explanation box, rho. How can we find volume charge density? Again, it's like with my case of my mass density. So how can I find my density? I take the total mass of myself, of me, and divide it by the total volume over which that mass is distributed. 100 kilograms divided by, 2 cubic meters, not probably too much, maybe 1 cubic meter, right? So in our case, we know the total charge Q is uniformly distributed over the whole sphere of radius r capital. That was given from the very beginning. Q divided by the volume of the sphere of radius with radius r capital. Okay, let me write it even explicitly. So it will be Q divided by 4 pi over 3 r capital to the power of 3. And again, it's another place. Remember these simple formulas for the volume of the sphere, area of the surface, area of the disk, circumference, because plenty of silly mistakes students make using just the wrong formulas. Okay, so now let's plug it, and let me write it first in terms of V. So it's a Q divided by V sub r capital and times V sub r small. So just plug it. And we're almost done. So let me write that explicitly. So it will be Q divided by 4 pi over 3 r capital, it's this part, and times volume of the Gaussian surface. Wait, r cube. 4 pi over 3 gets cancelled, and we have the answer. Q times r to the power of 3 r small divided by r capital to the power of 3. So that's what I usually do. Some students find the other way of writing it down easier to understand. I remember once I was explaining to one student in my office, and she kind of found, wow, it's easier. Okay, so now I usually start showing two methods. Let me show the other way of finding this Q enclosed. Right. Okay, let me write. Or it can be done like this. Okay, so let me write volume charge density. Again, by definition, volume charge density is what? You take the charge, total charge, and divided it by the volume over which that charge is distributed. Okay, so first let's use this way of finding rho using the total charge, because we know this total charge is distributed over the sphere with radius r capital. Just typical way of finding. So let me write that first. Q divided by 4 pi over 3 r capital to the power of 3. But how else can rho be found? Also, I can write also rho. Okay, you know what? I don't like this. Or how else rho can be found? Because we have uniform charge distribution. Charge density is exactly the same. Can we write rho in terms of Q enclosed? What if I write rho in terms of Q enclosed? I know that this Q enclosed is uniformly distributed over this sphere with radius r small. Right? So I can take Q enclosed and divide it by the volume over which Q enclosed is distributed. So I can write it also as this. Q in divided by now 4 pi over 3 r small to the power of 3. And this density and that density is the same because we have uniform charge distribution. So now I can, let me remove this or, I can put equal sign. And so now this and that part are going to give us. So from here, I can solve it for Q enclosed. Right. So this goes up here in the numerator, and we will get exactly the same answer. So it will be q times r to the power of 3 r small times r capital to the power of 3. Some students, when I explain this way, they find it easier to understand. Although, strictly speaking, I still that is pretty much as simple as that one, this option. Right? So you can use either this or that. Right? So that's the amount of charge. And look at the limits. For example, what will be the value of Q enclosed if R small equals to R capital? So here we'll have R capital to the power 3 R capital, so they will get cancelled, and we'll have Q enclosed will be equal to Q. Right? Makes sense, right? And if R small equals to 0, right, basically, well, in that case, Q enclosed will be 0, so it makes sense. Okay, so now, once we found Q enclosed, now it's time to plug it back to what we got from the Gauss's law and complete the problem. Okay, so now let me write so back to our Gauss's law. Oh, what we got from the Gauss's law, pretty much back to this point. Okay, so let me rewrite it with that expression for Q enclosed. So E times 4 pi r to the power of 2 equals, so it will be Q over epsilon naught and the ratio of these cubes. So r to the power of 2 r's over here and 2 r's over there can be cancelled, right? So this r goes over here, we'll get just one r, and so as a result the answer will be equal. So now we just need to solve for E, and now I will write E as a function of r. So it will be equal to what? Let me first write all constants. Q divided by 4 pi epsilon naught r to the power of 3 and 1 over r. Right? I think I didn't forget anything. So on purpose, I wrote a constant because all these Q 4 pi epsilon naught r to the power of 3, these are constant, and the variable is over there. Right? So no. I made a mistake. It's a numerator because here r to the power of 1, it's in the numerator. Sorry. Right. So that's for r small less or equal than r capital. So now let me frame it. That's part B. Yeah, part B is slightly more complicated because you need to spend a little bit more efforts finding Q enclosed. Okay, so the last piece, let me just plot how electric field changes with radius. All right, so what if I plot E versus R? And let's say this is the surface of the charge sphere. So inside, this is some constant. If R and Q, R capital and Q are given, so this will be just some number times variable R. So for R small less than R capital over here, we'll have a linear dependence. We'll have just a straight line. Electric field grows linearly. Right, so let me draw first this dash line. And now proportional to R. And now outside this. Again, Q over 4 pi epsilon naught, this is constant, and the variable is over here. It's a 1 over R squared. So it will be some kind of curve like that, parabolic. Okay, not parabolic, inverse. something like this, decaying as 1 over r squared. So this is over here proportional to r, over here it's proportional to 1 over r to the power of 2. So that's how electric field changes with r. Our electric field created by a uniformly charged non-conducting sphere, or for now we can say dielectric sphere, because if it were a conductor, the story will be slightly different. We will discuss that in a few classes, but for now, that's how electric field changes with time. Oh, not with time, with r, sorry. Okay, guys, again, if still something troubles you with this, okay, come to office hours or maybe after class, although every time I'm confused why students had troubles over here. It's barely a physics. It's sort of algebra with common sense and definition of charge density. And it's the same like mass density and finding the mass of if mass density is given. All right. So it's basically, I don't know, high school stuff. Beginning of high school, probably somewhere at that point. So we discussed spherical symmetry. There is another problem. It will be in the slides, in PowerPoint, okay, not PowerPoint, PDF file of my slides, right? So another problem will be like this. So again, you have uniformly charged sphere of radius, whatever, a. But inside of the sphere, there is a concentric hole. Look at that problem, right? So again, these steps will be basically the same. But finding Q enclosed, oops. But finding Q enclosed will be more complicated. Let me pick my markers. Dropped. So look at that problem. Look at that problem. You can make that problem even more complicated, but again, this part will be exactly the same, but finding Q enclosed will be slightly more complicated. For example, you have uniformly charged sphere, then there is a concentric hole, and at the center of the concentric hole, there is a point charge. Complexity in terms of finding Q enclosed, it will be minuscule increase in the complexity, but this part will be exactly the same, basically, right? Yeah, you can make this problem more complicated, but again, if you understand the principle of application of Gauss's law and idea of finding Q enclosed, all those, the increase in that complexity basically is not going to create significant amount of troubles. Again, if you understand the principle. So now we know how to apply it for in a different situations, right? So we know all the properties of the Gauss's law, and now, of course, we will start applying it everywhere it's possible, right? It's sort of like if you give a kid scissors, right? Then everything in the house will be cut in pieces, right? So we are pretty much in a similar situation, right? So now we have a new tool, and of course we're going to stick it everywhere it's possible, right? Okay, and we're going to use Gauss's law today a lot to explore properties of conductors. We need them. We need them a lot. Of course, in the electrostatic equilibrium. Of course, we will define all that in a second, right? Okay, it's still chapter 24. Yeah, these are sections. So first of all, we usually have three types of materials. Most likely you're familiar with those, right? So we have dielectrics, right? We have conductors, metals, right? And we have semiconductors. So semiconductors have tons of amazing properties. right? And that type of material deserves a separate course. And at some point, some of you will have courses about semiconductors, and you will learn about those amazing properties. All our electronics is based on their work, right? But in this course, we're only interested in insulators or dielectrics and conductors or metals. So first of all, we need to see the major differences major difference between these two types of materials, right? And then as a result, using this major difference, we can add additional properties of conductors, because we will need most of the time conductors, right? Okay, so first let's start with an insulating material, insulator or dielectric, right? It's that material where it's difficult to create current, or almost next to impossible, right? Right. So what happens? Let's recall classical model of an atom where you have what? A nucleus at the center, right? Which is positively charged, and then there is a cloud of electrons orbiting around that nucleus, right? And electrons which are closer to the nucleus, they are called core electrons. And on this picture, it's basically piece of a dielectric, and of course it consists of tons of atoms, right? And if you take one of these atoms, for example this one, you see at the center there is a red dot. That is a nucleus, right? And around the dot there are two circles, dark green and light green. Dark green represents core electrons, electrons which are closer to nucleus, right? So those core electrons, and electrons which are farther away from the nucleus, right? They are called valence electrons. Again, you see that those electrons are represented by those that light green color. Okay, so in a dielectric or in an insulating material, all those electrons, core electrons, valence electrons, they're all tightly connected. They're all tightly bound to nuclei, overall nuclei, right? As a result, basically, like they are prisoned, right? They cannot escape from their nucleus. Okay, not prisoned, probably they're sitting in their families, right? Right, and they don't go outside. Basically, as a result, this space between atoms, you see, we have tons of atoms, and space between them is gigantic. Lots of empty space, right? And that empty space is free. There is nothing. There are no free electrons. As a result, if you apply potential difference across a dielectric, there are no free electrons to travel, to create a current. Right? Yeah, the most what you can do, you can slightly distort these atoms, so electrons, maybe clouds of electrons can be slightly elongated in a certain direction, but that's the best you can do, right? So that's why it's difficult or almost next to impossible to create current in an insulating material, because there are no free electrons. They are all connected to their nuclei. Now, what about conductors or metals? It's a second situation, right? This picture. In this material, those valence electrons, right? You see valence electrons, those which are farther away from nuclei, they are weakly connected. They are weakly connected to the nuclei. And as a result, you can just slightly increase temperature over this metal, for example, from an absolute zero, right, minus 273 Kelvin, right? As a result, lots of those valence electrons will get loose and start drifting and start become free. They become free, right? And fill up that space between atoms. Even if you just sneeze maybe on that piece of a conductor, and a few additional electrons will appear, will become free, right? As a result, this piece metals has tons of free electrons. And as a result, if you apply potential difference across piece of a conductor, of course, those electrons, free electrons, will respond immediately, and they will start drifting in a certain direction, giving us what we call current. So that's why it's so easy to create current in metals. And of course, we use metals in our circuits, right? Because we can create current because of those free electrons. So as a result, the major difference between insulating material and conducting material, metal, that conductors have tons of free electrons. They are free to move whenever they feel like traveling, right? But in insulating materials, no. Okay, so now, knowing this major difference, we should be able to add additional properties of conductors. So now let's start moving, getting those additional properties of conductors. But again, this is the major difference. Right. Okay, so first, and since we just introduced Gauss's law, you can guess that most likely we're going to use Gauss's law in this lecture a lot. Okay, let's say a few times. Right. So first of all, let's imagine this situation, right? Just for fun. Let's take a piece of a conductor. Again, we're going to talk about conductors today only, right? A piece of a conductor, let's assume that this slab of material, piece of a conductor, and let's assume it is electrically neutral. What does it mean, electrically neutral? It means it has equal number of positive and negative charges. So as a result, overall, it's electrically neutral, right? And just for fun, let's expose it to some external electric field. For simplicity, I drew a uniform electric field, right? I know, maybe this external electric field is created by some gigantic capacitor, right? Maybe over here there is a positively charged surface plate. Over there somewhere there is a negatively charged surface. As a result, we have this uniform electric field, and there is a conductor inside. And so now our goal to see what happens to this conductor if you expose this conductor to this external electric field, right? And we just need to know only the major difference between the major property of a conductor. It has tons of free electrons. So what do those what are those electrons going to do? What will be their response to the presence of this external electric field? Of course, the question is reasonably simple. Let's imagine this is an electron inside of this conductor. Okay, barely visible, right? And of course, this electron is going to interact with this external electric field. And it is going to experience what? Electric force. F equals QE. You remember that fundamental equation? F equals QE. And since electron is a negatively charged object, electric force is going to point which way? Direction is going to be opposite to the direction of the external electric field. So it will be towards me, right? So the electron is going to start drift, is going to travel this way in the direction opposite to the direction of the external electric field, because it's a negatively charged particle, electron. So as a result, electrons are going to travel to this side of the plate, giving us, and of course they cannot jump over the border, right? We have a strong border control, right? So of course they're all going to be accumulated on this side of the conductor. And of course, since we have since the conductor is electrically neutral, if we have excess charge excess of negative charge on this surface, there must be positive charges on that side. So positive charges will be left behind. Okay, so now the question, of course, logical question. How many electrons are going to travel to this side, to this border, right, to this side of the conductor? 100, 1,000, 5,000, I know, millions, all of the electrons, right? And of course, you understand that the question actually is not about how many electrons will travel. Of course, the question is actually slightly deeper. Of course, the question is about the mechanism which is going to stop electrons from moving to this side of the conductor. What is the mechanism? At which moment electrons are going to stop drifting to this side of the conductor, leaving behind positive charges? Some students know that, some don't, and it's normal. Look, let's try to see what happens to this conductor once you first expose it to this external electric field. Okay, so we have first you put the conductor and position it inside of this external electric field. Of course, electrons start drifting, right? Giving us these negative charges and positive charges. What do these negative charges and these positive charges, what are they going to create? Can you see that? Look, physically, it looks like looks like a capacitor. So here we have a negatively charged surface, right? And here these positive charges creates like a positively charged surface, right? So we have a surface of negative charges, a surface of positive charges. What are they going to create? They're going to create their own electric field, blue electric field, internal electric field. This charge separation, it's called, basically it's called, we polarize the conductor, right? We induce charges. So these charges create their own internal electric field. And what's the direction of this internal electric field? Of course, from plus to minus, from positive charges to negative charges. So you see, this blue electric field is going to point in the opposite direction to the direction of the external electric field. So inside of the conductor, they battle, they fight, right? So external electric field that way, internal electric field in the opposite direction. And now, as I told you, let's just see what happens in time with these electric fields. So first, let's assume that a few electrons traveled to this side, right? So now a few electrons over here, a few positive charges over there, and internal electric field is reasonably small. A reasonably small internal electric field. Let me represent it with my finger, right? But external electric field is strong. So as a result, inside of the conductor, of course, this strong electric field is going to win, right? And of course, the net electric field, so basically net, it means you need to add this red field and blue field. Of course, net electric field will be still that way. And the electrons inside of the conductor, they still going to feel electric force, and they're still going to travel towards this negatively charged surface, right? So more electrons drift to this negatively charged surface, right? And as a result, it means that blue field, this blue internal electric field becomes stronger, right? So again, they battle, they fight with this external electric field. As a result, net electric field becomes somewhat smaller, but still not zero. It means electrons still feel the electric force and still travel. Increasing internal electric field. But if it's still smaller than external electric field, that electric field still not zero, and electrons still feel the electric force, and they keep traveling. So those electrons will keep traveling and traveling, keep drifting until what? Until internal electric field and external electric field equals to each other in magnitude, but of course they're in the opposite directions, point in the opposite directions. Right? As a result, what's the value of the net electric field at that moment when these two fields are equal? Electric field will be zero. And what will be the response of electrons once electric field becomes zero? They will stop traveling, because now they're not going to experience electric force. And they were traveling because they were pushed by the electric force. But now, once electric field is zero, they will stop experiencing electric force, and they will stop traveling. So charge separation at that moment will be stopped. Electrons stop moving, electric field zero, yeah, as I said, electrons stop moving. They basically like get settled, right? Buy a house, right? Get married and live happily ever after at that moment. They settled, their life is done, life is great, right? Electric field is zero. Right? So pretty much electrons will stop traveling when the electric field is zero. So at this moment, when this happens, electric field zero and electrons stop traveling, these conditions are called electrostatic equilibrium. Electrostatic equilibrium. Of course, you have to wait for a short period of time. Once you grab the conductor and expose it to external electric field, you will have to wait for a short period of time, maybe microsecond, maybe nanosecond, maybe picosecond. It depends on the material, it depends on mobility of electrons, but you need to wait for a short period of time because it will take for electrons some time to run like crazy, right? Trying to make an electric field zero. Right, and once they manage to make electric field zero, they get settled, yeah, and now the conductor is in the electrostatic equilibrium. So pretty much the job of electrons in this situation, they will keep running and running and running with the goal to make electric field zero. Otherwise, they will never stop running because they will experience electric force. That electric force will drive them crazy, right? Will keep pushing them. So that's what happens over here. But of course, and so from, okay, let me open a few. All right, so from now on, we're going to discuss conductors from time to time. And most of the time, we're going to assume tacitly, or it will be stated that conductor is going to be in the electrostatic equilibrium. So again, at that moment, electrons stop traveling, right? And electric field is zero. So the second major property of a conductor. In the electrostatic equilibrium, electric field inside of the conductor is zero. Right, again, otherwise electrons will keep drifting, keep moving, right? Okay, it's not a proof. It's more like a justification of this fact that electric field inside of the conductor is zero. So we need to remember. So now we know two properties. Tons of free electrons inside of the conductor, and in the electrostatic equilibrium, electric field is zero. Again, electrons, like brave soldiers, they will keep running and running, or athletes, and they will keep running until the electric field becomes zero. Right. Okay, so now next, what if, okay, in the previous situation, a piece of a conductor was electrically neutral. Basically, we had equal number of positive and negative charges. Now, let's make situation slightly more complicated. Let's take a piece of a conductor and dump some amount of, for example, positive charge on that piece of a conductor. All right, so let's say we have a piece of a conductor, and what if we, for example, at this point, dump some amount of positive charge? And now, makes sense to ask the logical question. Where does this, of course it's excess charge, right? We added that additional charge. Where does this excess charge reside in this conductor, right? A reasonably logical question. So let's ask that question, right? And let's try to answer that question now. So now it's not electrically neutral piece of a conductor. And again, we're going to discuss the situation. So we wait for a short period of time, right? Because who knows, for a short period of time, it will be a mass inside of the conductor, like in the previous slide, right? First, for a short period of time, it was a mass. Electrons were running like crazy, right? And we are going to wait long enough so that conductor reaches what is called, again, electrostatic equilibrium, right? And now, in the electrostatic equilibrium, we want to know where does this excess charge reside inside of the conductor. All right. Okay, so now, maybe you know the answer. But let's actually prove or show, yeah, where the charges are going to be. And you know what? Guess which law I'm planning to use to show this property. Since we just introduced Gauss's law, most likely that I'm talking about the Gauss's law. So let's apply Gauss's law to see locations of these charges. Right. Okay, so first of all, you remember whenever you want to use Gauss's law, what do you have to do first? You have to pick a Gaussian surface. Again, any surface can be used, right? Any surface can be used. All right, so I know, my soul desires, secretly desires to pick a Gaussian surface just below this surface of a conductor. Why not? I can apply it, right? Gauss's law is universal law, and it can be applied for any Gaussian surface. Okay, so I want to pick this Gaussian surface. Nothing and no one can forbid me from doing this. Okay, so now Gauss's law, right? We used it already a lot. And now look, so again, on this side we have a flux. There we have Q enclosed divided by epsilon naught. And of course, you see Gaussian surface. Can you tell me, what's the value of this electric flux? What's the value of this integral? Can you see that? What will be the value? Again, you remember I told you that we waited long enough to make sure that a conductor now is in the electrostatic equilibrium. So what will be the value of this integral? Okay, if you're not very confident, okay, let me push you. All right, so this Gaussian surface, and of course the integration is done over the Gaussian surface. Yeah, it's slightly below the surface, but it is inside of the conductor. All right, it is inside of the conductor. What's the value of the electric field inside of the conductor in the electrostatic equilibrium? We just discussed in the previous slide, right? It's zero, right? Electrons stop running, right? So their job is done. So they managed to reach their goal, right? Electric field is zero. So if electric field is zero, that the value of the electric flux will be zero because you integrate over the surface where there's no electric field. So electric field is zero, and as a result, our flux must be also zero. So it means that Q enclosed is zero. It means that Q enclosed is zero. Again, what is the meaning of Q enclosed? It's a charge inside of our Gaussian surface. And inside of our Gaussian surface, it's the internal part of the conductor. So immediately we conclude, so it looks like in the electrostatic equilibrium, it's impossible for the excess charge to be inside of the conductor. Nature forbid it, right? So we conclude that inside of the conductor, it's impossible excess charge. It's impossible for the excess charge to be. Of course, there is a charge inside, but it's an equal amount of positive and negative charges, right? So overall, internal part of the conductor is electrically neutral. We're talking about the excess charge, right? So we dump that a positive amount of charge. So now, if it's impossible for that excess charge to be inside of the conductor, where else it can be? There's only one place for them left to exist, right? On the surface. Okay, just below the surface, just outside of our Gaussian surface, right? So pretty much all that excess, positive excess charge can be only on the surface of the conductor. So now, again, it's in the electrostatic equilibrium, right? In the electrostatic equilibrium. So now we got the third property of the conductor. The first one, tons of free electrons. Second, in the electrostatic equilibrium, electric field inside is zero. And again, in the electrostatic equilibrium, any excess charge can reside only on the external surface, on the external surface, right? In this case. And conceptually, logically, it's actually easy to see. Because you remember, if you dump positive charges, for example, at this point, right? So what are those positive charges going to do to each other? They hate each other, right? They repel each other. If they repel each other, of course, they're going to run as far as possible from each other, right? And so what are the farthest points on the conductor? Of course, the surface Of course, these positive charges are going to distribute themselves somehow in a complicated way along the surface of a conductor, trying to be as far as possible from each other, right? It's a simple explanation, right?